What we're going to do in this section is we're going to talk about hypothesis tests for the difference between two means when we have independent samples. And we're going to start with an example. Scores on the National Assessment of Educational Progress, NAEP, mathematics tests range from 0 to 500. In a recent year, the sample mean score for students using a computer was 309, with a sample standard deviation of 29. For students not using a computer, the sample mean was 303, with a sample standard deviation of 32. And notice that they're telling you sample standard deviation. You know they do not have to tell you that. Assume there were 60 students in the computer sample and 40 students in the sample that didn't use a computer. We can see that the sample mean scores differ by 6, but we're interested in the difference between the population means. Like, based on this, the computer people scored 6 points higher than the non-computer people. But we want to know is what happens if the district goes to all computers? Is the population going to have a higher average? So we're asking, is it plausible that the difference between the population means could be 0? How strong is the evidence that the population mean scores are different? This is an example of a situation in which the data consists of two independent samples. Two samples are independent if the observations in one do not influence the observations in the other. I don't think that computer group has any impact on that non-computer group. They're not matched pairs. It's not taking the same people before and after type thing. Totally independent groups. In the scores from the NAEP, the issue is whether the mean scores from both populations of students, those using computers and those without, are equal. In other words, does mu1 equal mu2? Therefore, the null hypothesis says that the population means are equal. So HO for this is always going to be mu1 equals mu2. And your alternate hypothesis, you have 3 possibilities. I could say, like, if you look at that first one, I could say that mu1 is less than mu2. The computer people, the true population of computer people are going to have a lower average than non-computer. Or I could say mu1's greater than mu2. That would indicate the computer was higher. Or I could simply say that they're not equal. The way these are written is what Alex will do. I want to show you something that Minitab will do. So I want everyone to look at HO. Minitab will do this. It will say, okay, mu1 minus mu2. I move the mu2 over. Mu1 minus mu2 equals 0. Because if the two means are equal, their difference is 0. That's what that's telling you. Likewise, down at the bottom, this first one, I would say mu1 minus mu2 is less than 0. Okay? Second one, I would say mu1 minus mu2 is greater than 0. All I'm doing is moving the mu2 over, doing a little algebra on it. The last one, I would say mu1 minus mu2 does not equal 0. And I'm going to do the first ones I showed you. This is what we're going to do. I like these probably a little bit better, and that's what Alex does, but I want you to be aware of the others because of Minitab. Now, the next page is some stuff that we already did with a confidence interval. Mu1 and mu2 are the population means. X bar 1 and X bar 2 are the sample means. S1, S2 are the sample standard deviations. N1 and N2 are the sample sizes. The test statistic is based on the difference between the two sample means. The mean of X bar 1 minus X bar 2 is mu of 1 minus mu of 2. We're going to do it just like we did the confidence intervals. And I'm going to have the same assumptions. I'm going to have 3 assumptions. My first is that I have an SRS from both groups. My third is the normal condition. And you know you're going to have to do more than that to show that it's normal, but it's going to be something to do with normal. And the second are that the two samples are independent. In other words, I don't think what happens with the computer group has anything to do with the other. We're going to skip this page. I'm going to show you how to do the test on the next page. You can look back at this if you need to later. Now, here's the same problem that we just talked about, and they're telling us, can you conclude that the population mean scores differ? use the alpha equals 0.05 significance level. And we're going to do this as a complete test. So here's how we're going to start. We'll start with our conditions. They did an SRS. The two samples are independent. And for the normal condition, this time it doesn't say normal population or normally distributed in the story. So you're going to say N is greater than 30. The CLT tells us that the sampling distribution is approximately normal. And for both of these, you want to say both. I'm going to even add both here. What I'm going to do next, and this is up to you, what you write out at the end. But before we get to that, let's do our hypothesis. So let's do our HO and our H1. Now it says, can you conclude that the population mean scores differ? So H1 is going to be mu1 is different than mu2. Mu1 is not mu2. Note that this is two-tailed. The only reason I'm writing this is because when I interpret the p-value, I have to interpret it a little bit different. HO is always going to be mu1 is mu2. Mu1 equals mu2. And this is the part I like to write this. I like to write with computer and no computer. And I'm going to write my X bar 1, my S of 1, my N of 1, and ultimately you want mu of 1. And the same thing here. X bar 2, S of 2, N of 2, and mu of 2. Let's look back at our problem for a minute. Notice that this time they're telling you, we talked about before, they're telling you sample standard deviation. I know this is a 2-sample T. I also know they don't have to say sample. If it didn't say population, I would assume sample. Read back in your story. With computer, your X bar 1 is 309. Your S of 1 is 29. Your N of 1 is 60. Without computer, the mean was less 303, the sample mean. The standard deviation was 32. And the sample size was 40. And I'm going to go to the calculator and I'm going to do a test. And this is going to be a 2-sample T. This is a 2-sample T test. And I'm going to input my stats. And then just input that data. And just be careful as you input it. Notice it doesn't have a place for HO because HO is always going to be the same on these. But my alternate mu1 is going to be two-tailed, not equal. You're never going to pool. And I'm going to do calculate. Notice there's my test statistic and my p-value. I wrote out most of the information in the problem. So when I do my screenshot, I'm going to write up here just because of space. All I need to write out is what I did. I did a 2-sample T. And I'm going to write mu1 does not equal mu2. I'm going to write out my test statistic. Typically on that, you want 3 decimals for Alex. I'm going to do 3 decimals. I'm going to write out my p-value. You typically want 4 decimals on Alex. And you don't need your DF, but I'm going to write that too. And you can write that however you want. All right, and the rest of it I'm not going to write because I've already got it written in my problem. If the p-value is low, HO is going to go. This p-value is not low enough for HO to go. So here's what I'm going to say for my conclusion. I'm going to say since our p-value of 0.3434 is greater than alpha equals 0.05, we will fail to reject HO. If you fail to reject it, we do not have enough evidence to conclude and look back up in your story that the population mean scores differ. And when you interpret your p-value, I'm going to say if HO is true, there is a 0.3434 chance of a test statistic as extreme or more extreme. And where this is two-tailed, and I almost forgot to do it too, make sure you put a star there where it's two-tailed, because what you want to do that's different is you want to say as extreme or more extreme in either direction. That takes care of the two-tailed part. In either direction as ours, and ours is as t equals 0.343. I'm going to come back to this page. I want to go to and we'll talk about it, but I want to go to this last page. For this one, pause the video and read the problem and enter the data, treatment 1 in L1, treatment 2 in L2, and turn the video back on once you've done that. As I looked at this problem, I can tell that this is not matched pairs because I don't have the same number of items in each row. It doesn't say anything about going to a household and using treatment 1 and then the next month using treatment 2. This is a 2-sample t-test again. And what I want to do, it says, how strong is the evidence that the mean concentration is less for treatment 2 than treatment 1? All right, so here's what I'm going to do. My conditions are the same 3. SRS, both. 2, I'm going to do 2 first. I'm going to say both samples are independent. Now, I need to do a graph of both of these, and this is something we've not done for a long time. I think we did one the first week of school, but it's been a while, so I'm going to show you how to graph both of these at the same time. So here's what I want you to do. Go to your stat plot and turn on your first one. You know how we always do that one. And I'm going to do zoom 9. So there's my first one, okay? Now, I'm going to turn the second one on at the same time because I need to graph both of them. So I want you to go back to your stat plot. I want you to go to the second one, okay, the second graph. You can plot a whole bunch of graphs on your graph at the same time. And I'm going to turn it on. Now, I want to do same thing with this, box plot with outliers. And I want to pull my values from L2 because treatment 2 is in L2. And L2 is on number 2 on the calculator. Hit second 2 and hit enter. And hit zoom 9. And both of those graphs should come up. And if you need to go back and do it again and make sure you can get both graphs to come up. All right, so here's what they look like. I'm going to do a screenshot that looks kind of like this. Doesn't matter a whole lot, but you want it to look similar. Like I wouldn't want these 2 box plots to look identical. Okay, so it looks something like that. The red one has a lot more variability. You can tell from how it's more stretched out. It's got more variability for treatment 2. Here's what I'm going to say. I'm going to say no outliers or strong skewness. Normal, check. And you can say both graphs. If you don't say both there, you're fine because I see both. All right, and now I'm going to do the test. Now, I want you up here for a minute. Notice that this test says how strong is the evidence that the concentration, the mean concentration is less for treatment 2, mu2 is less than mu1. This is perfectly fine, but Alex and not Alex, well, Alex too, but the computer, the calculator, and Minitab sees this as backwards because they want mu1 on the left. So what you want to do is flip this around and say mu1 is greater than mu2. Okay, that's the same thing. Notice that I flipped it. I flipped the inequality. The big part of the inequality is still facing mu1. This is that switched around. And this is what I need to use for my H1. I needed to use mu1 is greater than mu2. HO is going to be mu1 equals mu2. Now, I like this one because you're going to go to stat test and you're going to do a 2-sample t-test. And you've already entered your data. Notice I've not written any numbers. I'm going to go to data, and I'm just going to pull it up. I'm going to pull it from L1 and L2, do nothing with frequency. And my alternate hypotheses, notice how they're asking for mu1. That's why you have to flip it. It's mu1 is greater. And I'm going to calculate it. All right, and that's what I get. Now, notice I got a lot of stuff going on. I didn't write anything. So this time I need to do a complete screenshot. On the ones like this that you do on the calculator, I would always do like this. Right, so I did a 2-sample T, mu1, and then just take a minute, and you can pause the video if you want or leave it on. Just write everything down. Look at your p-value. And look at our p-value. If the p-value is low, HO is going to go. This is not low enough for HO to go anywhere. So here's going to be my conclusion. I'm going to say since our p-value of 0.0719 is greater than alpha equals 0.05, we will fail to reject HO. We do not have enough evidence to conclude and look back up at your story that all you need to add is true, that the true mean concentration is less for treatment 2 than for treatment 1. Notice I didn't switch it. You don't have to. That's perfectly fine. We just switched it because of the calculator. When I interpret the p-value, I'm going to say if HO is true, there is a 0.0719 chance of a test statistic as extreme as ours. And ours is as t equals 1.590. All right. And let's go back to that page that we skipped. I want you to look at the Minitab output just for a minute, and we'll do more of this after next week, but I want you to just look at this for a minute. What I like about Minitab is it does the tests and the confidence intervals in the same thing. And I want you to look at this. There's the confidence interval if I needed it. Difference mu1 minus mu2. And look at how they list your HO. Theirs is test of the difference equals 0. Okay, so this is what their HO is. Their HO is, they're listed as mu1 minus mu2 equals 0. Mu1 minus mu2 equals 0. We would list that as mu1 equals mu2. Both are fine. Their H1 is versus not equal. So their H1 would be this. Mu1, the difference, minus mu2 is not 0. Ours would be mu1 is not 0. I mean, mu1 is not mu2. Sorry. I don't like how Minitab rounds. There's their test statistic, their t-value. I like 3 digits. There's their p-value. I like 4 digits. But again, it would be the same thing as the calculator. And I want you to do this next problem on the calculator. It's a little hard to type in. We're not going to formally do that. We're going to pretend this is just drop down menu in ALEKS, and I just need to answer what's the value of the test statistic, and am I going to reject HO? And I'm going to do this one without writing anything, and it talks about everything, all the conditions being met. But I'm going to do stat test, and I'm going to do a 2 sample T. And be careful with this one because it's not in nice order like how I usually list it. So I'm going to go to stats, and I'm going to input my data. X bar 1 is 73.9. Now I want S of 1. S of 1 is 4.2. N of 1 is 23. Just be careful because you see how I'm all over the place. X bar 2 is 71.8. S of 2 is 3.8. N of 2 is 17. And my alternate hypothesis is not equal to. It's two-tailed. Remember, if I had to interpret P, you're not going to have to for here, but if I had to interpret P, it's two-tailed. It's different. Okay, and then I'm going to calculate it. All I want is my test statistic. My test statistic is T equals 1.652. And I want to know if I'm going to reject HO. My p-value is 0.1072. That's a big p-value. HO is not going anywhere. I'm going to fail to reject. Now, hopefully we didn't make any errors today, but on every one of our conclusion, we have failed to reject HO. So if we made errors on anything today, we made a type 2 error because we failed to reject. We did not make a type 1. We couldn't have. If you fail to reject, it could be a type 2 error. And if you look back at our problems, that's what we did on each of our problems today.